and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 4, Lesson 4 on dilations in the coordinate plane. So far, we've worked with dilations on a sort of one-dimensional number line. That's how we started. In the last lesson, we worked with some dilations that were just sort of in what we call the Euclidean plane. There's no grid, no coordinates or anything like that, and for that, we had to use a lot of rulers to really kind of like measure things and then multiply by our scaling factor to make them longer or shorter, etc. In the coordinate plane, where we have both the x and the y-axis, we can do a lot of dilation work simply using coordinates themselves. At the same time, though, we will continue to talk about things like the center of dilation and, what's really important, the scaling factor or the constant of dilation. So, anyway, let's get right into it right now. Make sure you have a straight edge for this because you're going to need it for quite a few of the problems. All right, here we go. Let's start in exercise number 1. Point A below has coordinates of 4, 3. The origin, 0, 0, is marked as point O. We want to find the image of A after a dilation by a scale factor of 2 with a center at the origin. All right, now remember what that means. All of that means, saying that we want to do a dilation of this point using this point as its center and a scale factor of 2 means that we want to make this point twice as far away from the origin as where it started, but in the same direction. All right, so letter A, very simple. Draw ray OA. All right, so let's do this together. This is no problem. In fact, it's going to be more of a problem for me than it is for you. But as you draw these rays in the coordinate plane, try to be as careful as possible because if you misdraw even a little bit, the ray won't go through the points that we need it to. So here's our ray OA. Right, which establishes the direction, right? That's kind of really what rays do, is they establish a direction. Now, what we know for certain then is that the image of A, which should be somewhere out here, right? The image of A is going to lie somewhere along that ray. So let's take a look at exercise B. Given that A prime, the image of A after the dilation, must lie on ray OA, at what coordinate point do you believe it lies? Mark it on your diagram and fill in the mapping diagram. All right, so I'd like you to do that. I'd like you to try to figure out where along this ray A prime must lie given that it's got to be twice as far from the origin as where it started. Pause the video now and just play around with it a little bit. See if you can figure out a method for getting there. All right, well, one kind of cool way of thinking about where A should lie is saying, well, all right, if I were at the origin and I wanted to go to A, I would walk sort of 4 units over and 3 units up, all right? Therefore, if I want to sort of double the distance, I can walk 4 units over and 3 units up, and I will be 1, 2, 3, 4, 1, 2, 3. I'll be right here. And of course, that's got coordinates at 8, 6. All right, now, letter C simply asks us, why do you believe it lies at these coordinates? So take a look just for a second at 4, 3 and 8, 6, and the fact that we have a scale factor of 2. So hopefully it's kind of obvious. Why do we believe that it lies at these coordinates? Well, because both the x and the y coordinates are double what we began with, right? And that makes sense because we have a scale factor of 2. Let's write that down really quickly. All right. So both the x and y coordinates of the image point are twice those of the original. Now, let's make sure that you understand this idea, because it's pretty darn easy. When we're dilating points in the coordinate plane with the center at the origin, and oftentimes the center is at the origin, we can just dilate both the x and the y coordinates using the scaling factor. So if I start with the coordinates x comma y, and I've got this scaling factor of k, then I just do k times x and k times y. It is so easy. I mean, the x and the y coordinates indicate the distance, now granted the horizontal distance and the vertical distance, but x and y indicate the distance that the point is away from the origin, and also with some directions given the negatives in there, right? So as long as I multiply both of those two sort of distance coordinates by my scaling factor, then my point should lie that much farther or closer to the origin. So let's play around with this a little bit in exercise number 2. Let me just get it up to the top of the page and let's take a look at it. For triangle ABC, do the following. Plot the image of triangle ABC after a dilation by a scale factor of 2. Label it as triangle A', B', C'. State the coordinates of the image's vertices below. All right, so it's really this easy. Let's do it for A together and then have you do it for B and C on your own. So here we've got point A, right? And it's at coordinates 2, 4, right? 2, 4. Whoops. 2, 4. And we know we have got a scale factor of 2, right? Scale factor of 2. So A prime is going to be 2 times 2, 2 times 4, which gives me A prime at 4, 8. All right, so let me go ahead and plot that. Here's my A prime at 4, 8. All right. What I'd like you to do now is do exactly the same thing with B and C. Now C might be a little bit more challenging because there's some negatives involved, but remember, if you multiply a negative by a positive, like 2, right, it remains negative, all right? It's not going to suddenly switch to being positive. So pause the video now and go ahead and do that. All right, well, we have B at 4, 1, so B prime, when I double both of these coordinates, will be 8, 2. All right, 8, 2 for my B prime. And my C, which is at -3, -2, when I double both of those coordinates, my C prime will be at -6, -4. All right, so right here. And of course, I want to connect those all with straight line segments, easier for you than me, but we'll take a shot at it. And a little bit of this. And finally this. This is the one that's tricky. But move it over here. And we've got triangle A prime, B prime, C prime. Right? There it is. There's our dilated triangle. And of course, it's gotten bigger. And the reason it's gotten bigger is because our scale factor, remember, is larger than 1. Never forget that. When we have a scaling factor that's bigger than 1, then all distances will get larger by that factor. And when we have a scale factor that's less than 1, all distances will get smaller by that factor. Now, letter B, this is important, right? Letter B asks us to state the value of each of the following ratios. So the first one asks us A prime B prime divided by AB, and the second one is BC divided by B prime C prime. Now, you might think to yourself, well, that doesn't seem very fair. I don't know the length of A prime B prime, and furthermore, I don't know the length of AB. Right? And that's what these are. Never forget, if we don't have a segment marking over those two letters, it means the length of the segment. So how can I really say what this ratio is if I don't know the lengths of those two segments? Pause the video now and think about that a little bit. How can I come up with these two ratios if I don't know the lengths of the segments? Well, the whole point of the scaling constant, right, 2, is that is the ratio of the new lengths divided by the old length. So in this case, this is the new length, right? A prime, B prime divided by the old length, AB. And so its ratio must be 2. It's got to be K. All right. Now maybe a little bit trickier is the ratio of this older length, right? BC was an original length. It's this one, right? What is that length compared to its image, B prime, C prime? Pause the video now and see if you can think about what that ratio must be. Well, think about what this really means. A prime, B prime divided by AB is 2. That really means that the image is twice as long as the original. But this one is, right, the original divided by the new one. That ratio then is the reciprocal of this one. That's got to be half, right? And that will always be the case, right? So if we had a scaling constant of 3, then that would mean that the ratio of the new length to the old length was 3. 3 times as great. But the ratio of the old length to the new length, that would be 1/3, right? Because the old length is only 1/3 of the new length. All right, this is a very important idea, so make sure that you have that before we move on. Speaking of which, let's move on. Let's do some more dilations in the coordinate plane. Exercise number 3. In the diagram below, triangle MNP has vertices at M 3, 9, N 6, 0, and P -6, -3. Under a dilation with the center at the origin, point N gets mapped to point N prime at 4, 0. Letter A. Was the scaling factor used to map N to N prime greater or less than 1? How can you tell without calculating its value? Awesome. Pause the video now and see if you can answer these 2 questions. One, was the scaling constant greater than or less than 1? And then the second one, how can you tell? Pause the video now. Well, let me move this out of the way for a second. It's really important to understand, right, the original point out here versus the image point right there. And notice the image point has actually gotten closer to the center being the origin, than the pre-image or the original point. And therefore, because the distance got smaller, this thing must be less than 1. So, less than 1 because the image got closer to the center. There we go. The image got closer to the center. All right, it's that simple, right? The original point was 6 units from the center, and the image point is 4 units from the center. That being said, let's take a look at letter B, right? Letter B asks the following. Find the value of the scaling factor K to verify your answer from part A. All right, how do we find the value of the scaling factor? Pause the video now and see if you can figure this out. All right, well, here's the key, right? The scaling factor will always be the distance from the center to the image divided by the distance from the center to the original point. Well, we know the distance from the center, the origin, to the original point, and yes, that's point N, is going to be 6 units, right? It's this distance. On the other hand, the distance from the center to the image point is 4 units. It's this distance. And therefore, the scaling factor, remember, is always the new distance divided by the old distance, and that's going to be 4 divided by 6, which reduces to 2/3. And of course, 2/3 is a number less than 1, right? Never forget that you can always calculate the scaling factor by taking a new distance or length, right, divided by the old distance or length. And the new distance is always the distance or length in an image, right, in a sort of a prime, if you will, versus the old, which is just what you started with. All right, so we've got a scaling constant of 2/3. And predictably now, let's look at letter C. Letter C says, map the rest of the triangle using the center at the origin and the value of k from B. Label the image triangle, triangle M prime, N prime, P prime. Show where points M and P map below. All right, great. Well, look, you already know how to do a dilation in the coordinate plane. You just need to take these sets of coordinates, and because the center's at the origin, that's key, you just need to multiply all the coordinates by the number 2/3. So pause the video now. I will say I made all of these work out nicely. So all the coordinates should be whole numbers, with some negatives, obviously, in the case of point P. Pause the video now and see if you can figure out where those 2 points get mapped to. All right, well, let's go through it. Let me move this out of the way and maybe move my ruler out of the way, and then maybe even give myself some new room, right? Because what we really need to do is we need to take these 2 coordinates and we need to multiply them, maybe I'll put it over here, by 2/3. So 2/3 times 3, right? That's going to go in once, and that's going to be 2, right? And 2/3 times 9, that's going to go in 3 times, and that's going to be 6. So M prime is going to be 2, 6. Let's do the P. Let's do 2/3 times -6. That's going to cancel, giving me a -2, and -2 times 2 is -4. And then I have 2/3 times -3. 3 will cancel into 3 one time. 2 times -1 is -2. So P prime is -4, -2. All right, let's graph those. We've got M at 2, 6, or sorry, M prime at 2, 6, and P prime at -4, -2. Maybe I'll just draw an arrow up there to P prime. And I think I'm just going to end up sketching these things in now by hand to save ourselves a little bit of time. And again, predictably, we're ending up with a triangle, or the image of a triangle, that is smaller than the original triangle because that dilation constant is smaller than 1. I mean, it's just like taking a picture on your phone, right? And then shrinking that picture down, right? By multiplying all the coordinate points in it by 2/3. It's kind of cool. Let's keep going. One more problem. Now, so far we have dealt exclusively, right, with these dilations in the coordinate plane where the origin is the center. It gets much harder if the origin isn't the center. But you can still do it given what you know. So let's do one of those in exercise number 4. On the diagram below, segment EF has been plotted along with point G. We would like to dilate EF using G as the center and a scaling factor of 3. Letter A asks us to carefully draw rays GF and GE. Okay, so let's all do this together. Now again, I want to do this as carefully as possible because these image points are going to end up lying on these 2 rays, and so if my rays themselves are a little bit messy, it's going to be pretty hard to get everything else right. All right, so I'm going to do my best here to draw ray GE. All right, and now we will try to get a good ray GF in. All right, and then we will get our ruler out of here for right now. Okay, great. So our image points lie on these rays, okay? The question is, where are they? Now remember, this is our center, and we have a scaling factor of 3. So let's take a look at letter B. Use the distance and direction that F and E are from point G to find their images, E prime and F prime. Show the mapping below. All right, so let me explain what I mean by, using the direction and distance they are. Okay, point E, I can get to point E from point G by going down 4 and to the right 1, right? So what I want to do is I want to do that 3 times, so my point G prime ends up being 3 times the distance, my point E prime ends up being 3 times the distance from G that E started with. Literally, I'm going to go down 4 to the right 1, 1, 2, 3, 4 to the right 1, 1, 2, 3, 4 to the right 1, right? And there is my E prime, and its coordinates are 1, comma, -4. Okay? Why don't you try to do the same thing to locate where F goes? All right, well, F relative to point G is 3 units over and 1 unit down. So I'm going to do that 2 more times. 3 units over, 1 unit down, 3 units over, 1 unit down kind of thing. 3 units over, 1 unit down, 3 units over, 1 unit down, and there's my F prime, and it's at 7, 5. All right, now I want to draw the segment in as well because I'm dilating the whole segment. It's just that if I dilate the endpoints, then that will be good enough. But I want to get the segment drawn in there. And there's my segment, E prime, F prime. Now, even though it's not part of the problem, I want to remind you something about dilations. Whenever we dilate a line segment, right, with a center that's not on the line segment, the image that's produced has been scaled the same amount as the distance of, or the length of that segment, plus it's parallel to it. And you can kind of see that a bit. I mean, maybe we would want to draw, line EF in more, but it should be kind of obvious that this segment and this segment run parallel to each other. But let's take a look at the last part of this problem, because this is kind of cool. We can actually verify that E prime F prime is 3 times the length of EF without calculating the length of either one of them. So let's take a look at letter C. Illustrate using the length and direction of segment EF that its image, E prime F prime, is 3 times its length. Well, this is kind of cool because we're going to do something very similar to what we did when we dilated these points. We're going to say, look, if I look at E and F, right, to go from E to F, I would go 2 units over, right, 1, 2 units over, and 3 units up. Watch what happens when I do exactly the same kind of 2 over and 3 up path to get from E prime to F prime, right? So if I go 2 units over and 3 units up, I'm right here. 2 units over, 3 units up, I'm right here. 2 units over, 3 units up, and I'm right here, right? So literally, I can take this particular line segment and reproduce it 1, 2, 3, right? That length and direction, 1, 2, 3. That second one looked a little bit small, but it's fine. Yep, yeah, 3 times the length. And that's what dilations always do. Regardless of whether we're on a one-dimensional number line, whether or not we're kind of in the Euclidean plane where there's no coordinates, or we're in the coordinate plane where we can use these nice numbers to really kind of know where everything's at, the plain fact is when we dilate a line segment, the image ends up being, the 3 times the length of the original, or k times the length of the original, and runs parallel to it. All right, let's wrap this up. The coordinate plane is a fantastic place to do dilations, especially when their centers are at the origin. Because if the center of a dilation is at the origin in the coordinate plane, then all we have to do is multiply the x and the y coordinates by the dilation constant. It does become more challenging if the center isn't at the origin, but as we saw in the last exercise, we can still do it. Now we're going to be working a lot with the coordinate plane and dilations in the coordinate plane in future lessons, so make sure to really kind of pay attention and work hard on the homework tonight. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.